Alright, so this is the AP Physics for the energy test. This is going over the solutions for the review sheet. This is the rest of the questions, 11 to 20. Sorry about the first video, took too long, so I'm going to try to make this one short, okay? Alright, the work done by stretching, here, let's zoom this in. The work done by stretching a spring, ideal by 40 centimeters. Ah, stupid, look, it's centimeters. Alright, centimeters. I need to convert that into millimeters. Okay, so that is 4.0 times 10 to the negative 2. So this, so the x is 0.04 meters. Okay, if you want to know how to do that, I went 40 centimeters. Oops, centimeters times, okay, 1 centimeter meter, okay, and this was 10 to the prefix gets the 1, so the prefix gets the 1. This is 10 to the negative 2, okay, cancel, get you 0.04 meters, okay. That's how I did that if you want to see. Okay, all right. What is it's joules, so work is equal to 6.0 joules. What is the spring constant? F. What spring constant, question mark. So work, what, so the work done by spring, what is the spring constant? Well, hold on, let's see if I did it right this way. Hold on. Probably work is probably going to be the change in potential energy, which is just, in this case, it's 1/2 kx squared, because this is the um, spring constant here. Work, I have work here, so let's see if this works. I want k, right? So 2w is equal to kx squared divided by k goes to x square root this this. Oh, no, sorry. I'm looking for the spring constant. So, divide that by kx squared. Yeah, this looks right. Okay, let's see if it works. Because that's the deviation for it. Okay, so do you work is what? 6 joules. X is 0.04 squared. Get you the k. 2 times 6 divided by 0.04 squared. Yeah, that works. Got me K of 7,500 newtons. So, yep, that works. An ideal spring has a spring constant of 600 newtons. How much energy does it store when it is stretched by 10 centimeters? Again, why is it 10 centimeters? 10 centimeters is converted to 0.01 meters. Okay, you want to see that? That is 1.0 centimeters. Meters, centimeter. The prefix gets the 1. Cancels, gets you 0.01 meters. Okay, there you go. That's the conversion if you want to see it. Alright, so let's just grab a couple of things. How much energy does it do when it's stretched there? So I need to know how much energy. So that is energy. I need joules, so that is energy, right, is going to be equal. It's going to be the delta U. Okay, so this is going to be energy, right? The summation of the energies is that. So the final is just going to be 1/2 kx x squared. Yeah, so it's just 1/2 k, which is what, 60 newtons, centimeters, 0.01 squared. This gets you its energy. So this is what, how energy, 1/2 times 60 times 0.01 squared. Yeah, I mean, unless I'm wrong, I got 0.003 joules of energy. Yeah, doesn't seem wrong. Okay, if I'm wrong, please leave me a comment but yeah, that seems like it works. How much work is required to stretch an ideal spring with a spring constant from there to there if the unstretched positioning is at x equals to 0? Man, there might be a shortcut, but I'm going to do this the long way. An idea. What? Oh, so how much work is required to stretch? There's no gravitational potential. There's no kinetic energy potential. So energy, in this case, right? Right. The is just going to be delta E, no, delta U for the spring. So it goes from 1/2 kx squared is equal to 1/2 kx squared. Again, this is initial. This is its kinetic if the unstressed positioning is 0. Yeah, yeah. And kinetic 2. Okay, so it's how much work is done. Oh, you wouldn't have to bring this to the other side. Okay, because final minus initial, right? Do you see that? Okay, so its final was 2. So delta E is going to be equal to 1/2 kx squared 2 minus 1/2 kx squared initial. In short, 1/2 k x squared of 2 minus x squared of 1 will get you your energy. Okay, so it's 1/2 k times 0.25 squared minus 0.2 squared. All right. Oh, let's see. 1/2 times 40 times 0.25 squared minus point squared. Yeah, got me 0.45 joules. That is my energy. Okay, again, that is what energy is, the delta of the U's. So that is A. Okay, 14. And ideal spring constants there. So that's K equals to 15 Newton meter is compressed by a, damn it, still centimeters. So 3 centimeters is converted to 0.03 meters. You want to see it done? Just check the previous problems. I show how to convert it. X is equal to 0.03 meters. How much work is done to compress an additional 40 is initially compressed by 30 centimeters. How much work is required to an additional 40 centimeters? So this is the first one. The second one is 0.04 meters. Okay. So again, summation of the E, right? It's just the energy is the work. Summation of the energy or the work. Okay. Right. That's just work is equal to delta U, which is just, in this case, 1/2 kx squared minus 1/2 kx squared. Oh, we already know what this is. This is 2 minus 1, so it's 1/2 k x squared minus x squared initial. No, this is final minus initial. Okay. If you don't like that, 2 minus 1. Yeah. So it's 1/2. What's k times 15? Its final is, so it's 0.4 squared minus 0.1 squared. Oh, squared. So 0.5 times 15 times, what is it? 0.04 squared minus 0.03 squared. Oh, uh, something's off. 15, 15. 1/2 15. Compressive spring final, because this is what I got. Okay. 0.0525. Doesn't look like it's in here. Spring constant's here. It's initial compress by 30 meters from its uncompressed positioning. So that is its initial. Oh, this should be a 3. So let's try that again. A half times the spring constant. The final is squared and then minus the initial. This is interesting. I might be wrong here. Now I'm getting a different answer. I got roughly 0.0035. Not sure I can go with this value. Looks close, but might be off. How much work is done to compress? I could have done it this way though. I could have just 1/2. Wait, what? No. Hold on. Work is just force times um distance, right? The distance here is really the distance here is 0.1 because it's going from meters, right? Because it's going from there to here. I just need a force, uh, which is just this, right? Would that be work though? Work is just force times a distance. Would that work? No, that wouldn't work. No, that wouldn't work. This is work, right? How much work is done? Because I know work is force times distance. What is the work that is being applied? Uh, Work done by the spring. Um, which is just no, that wouldn't work. Yeah, that wouldn't work. That wouldn't work. Yep, that is wrong. It would have to be using the energy equation. The closest is gonna be probably D. Give me a second, okay? Paul. All right. So I just double checked it. Yep, it's right. 15. Let's see here. Joules stretch from here to here from equilibrium. What is the value of the spring constant? Same thing. So work is equal to 87 joules. Its x initial is 1.4 meters. X2 or x final is 2.9 meters. Work is going to be equal to the delta U, so it's 1/2 kx squared second minus 1/2 kx squared initial. Simplify, it's 1/2 k x squared minus x initial squared. 1/2 k is no. I'm actually asking to solve for oh w wait. Value of the spring constant is okay. So multiply this by 2, so that becomes work is equal to k x squared minus that. Divide that over, so it's 2 of the work divided by kx squared minus k initial here. Parentheses equals to k. So it's twice, 2 times the work divided by the change squareds. Okay. So here it got me 2 times the work is 87. Okay, divide that by 1.5 squared. Gets you the answer of 77. Okay. Good. Let's go up here. Hopefully this video is shorter. Okay. A roller coaster starts from initial. Okay. From height h on this LSF side shows, and it swings around there, and it needs to maintain a certain. What is the height for it to maintain there? Okay, so we need from here. We basically need it from here to here, and we need a height. Remember, we had a velocity equals to square root g8 gr here. Remember, because this is the minimum velocity, so that it still goes over. If you remember from your review sheet from last chapter, you're gonna need there. Okay, so yeah, okay, so roller coaster problem. I know this is always my kinetic, so energy 2 is gonna be equal to my energy 1. Or in this case, I'm just gonna go energy initial is going to be my energy equal to my final. Okay, so right, so I have mgh plus 1/2 mv squared. Uh, so let me just do it all from scratch. us plus ug plus k is equal to us plus ug plus k. Okay, there's no spring. Okay, there's no kinetic at the start. Okay, and there is some potential because there is a height. So, okay, from there, now you plug in its values. mgh is equal to mgh plus 1/2 mv squared. All the masses cancel out. You have gh. Please understand this is height 1, this is height 2. They're not the same height. So gh2 plus 1/2 v squared. All right. Solve this over. Subtract it over to the other side. Oh, I can multiply this by 2. Screwed it. Yes, technically you can pull it out. Okay, so this in short says that, okay, square root 2g delta h, right, is equal to its velocity. Okay, that's what it says. Let's see. Square root. Just plug in the values now. What is the height? So height here is 6 meters, 6 meters. So the height here, h2 is equal to 12. Okay. So, shoot. I need height final. This is useless. Hold on. This was all horrible. I thought I wanted the height. That's horrible. Okay. I wanted what height 2? I have height 2. Let's hold on. Let's go back here. I want height 1, right? So h1 equals to gh2. Wait, hold on. So hold on. I have this. Let's just go back. I have this. Okay. All I'm gonna do now is just divide by g. Divide this by g. Height h1 is equal to g, which is just 10, times height 2, which is 12, plus 1/2 velocity. I know my velocity here. Okay, velocity is gr. So this is going to be times gr. Why? Because look, if I plug it in, square root of gr squared This cancels. It just becomes GR. If you're wondering how I just got that GR. But I know what my GR is though, right? So it just becomes 1/2 G is 10. What's my R? 6 is divide this by G, which is just 10. So just plug that in. 10 times 12 plus a half times 10 times 6 divided by 10. Yep, got you 15. Okay. That is if you want to see the work. The hard part is converting the v squared final is equal to v here is the square root of gr. Okay. Here a bead is moving with a speed of 220 meters per second at the position A. So v initial is actually 20 meters. What is the speed v final? There's no spring constant, okay? Please understand. Energy 1 is going to be equal to energy 2. So it's going to be U plus K equals to 1, 1 plus U2 plus K2. U, it's mgh. There is a height, there is potential energy. Yes, there is actually still kinetic 1/2 mv squared 1. Yep. To, what is its speed? So it's 1/2 mv squared. This is 2. Okay, the reason why this still exists is because there's velocity and everything here. There's a shortcut for this, just letting you know. Okay, masses go away. Okay, subtract everything over. So it's GH minus GH2 plus 1/2 v squared 1 equals to v squared 2. Okay, technically what this, okay, so 10 times, what's the height? 200 meters, subtract 10 minus what? 160 plus 1/2. V initial is 20, square that is equal to v squared. Okay. So that is 10 times height, 20 meters, subtract 10 times 160 plus a half times 20 squared. Yeah, 600, but I have to square root the final answer. Because I got something like 600 is equal to v squared, right? But you see how you have to square root it? Speed is 24.49. Hold on. Give me a second. Let me pause the video. I want to check my errors, okay? Okay. I made a mistake here. You, shoot. Look, watch this. This whole thing is wrong. I was looking over my work. Here, look. I went too fast here on the deviation. So I subtracted over this. Okay, so I subtracted this over, right? I should still have this. MH minus GH2, this is 1, plus 1/2 v squared 1 is equal to 1/2, right? There's no m though. v squared 2. I have to still multiply by 2, so this becomes 2 gh1. I could do 2 of this gh minus gh, right? 1, 2, plus 1 half v squared is equal to v squared 2. Yeah, okay, that works. That works. This makes more sense. I should square root it, but I'm just going to leave it right here, okay? I'm just going to find the value of this first, okay? So let's just plug this in. There's a this can just become like 10 times, what is this? h1 minus h2 just becomes like 40 meters plus 1 half. 20 squared is what? 400. Okay, I'm just plugging it in. So let's see. This becomes what? 400 plus this becomes 200. Yeah, times 2 is going to be squared v2, so this becomes 600. V squared 1200 equals to v squared 2. Square root of that gets you v2, so that's the square root of. Yep, there it is. That makes more sense here. That would be at 64 meters per second. There it is. Okay, this is a very famous question. So try to do that as best as you can. Okay, I made a couple mistakes, went back and fixed it. So follow this as best as you can. Alright, Joe identicals balls 4. Joe throws his ball with initial speed twice as high as Bill. There's no air resistance. The maximum height of Joe's ball would be what? Okay, so here's Joe. Okay. Joe throw the same identical ball vertically upward. Joe his ball with initial speed. So Joe throw it twice at with an initial speed twice as high. Throws with initial speed twice as high as Bill. The maximum height of Joe's ball will be what? This is weird. Hold on. I get it. There's going to be a kinetic energy here of 1 half mv squared. Okay, and it's all going to be converted into a mgh. So if you want to think about it in terms of initial, so this is your initial picture, and this is going to be your final picture. Okay, so at original it's 1 half mv squared, and your final is just mgh, right? Ignore the m's. Okay, and the h's are and the g's are the same in both scenarios, and the halves are the same. Okay, it's a function here is going to be a the height is a function of going to be a function of velocity squared. So if he throws it with an initial height, that is twice. So if you twice the velocity, 2 velocity squared equals to the height, it becomes v comes that. Okay, so it's gonna be 4 times. So if you double the velocity, your height goes up 4 times because velocity is squared. Okay, it is squared. It's squared. Yeah, not proportional. It's not directly proportional. Okay, a stone ramp. It's down 4 different frictional. Is there only 4? Uh, there's only 3. There should be 3 frictional ramp as shown. For which ramp is the bar the greatest? What for which ramp? So it's a trick question. The answer would be D. Okay. The path don't matter. So the path don't matter. Okay. So the height here can be like, let's say the height here is 20, right? Meters. Height H is 20. Height final is equal to 0. If you work it out, it's going to be the same thing as mgh is all going to be converted to 1 half mv squared. So your velocity is going to be defined by this. Gravity and height. So if you really want to think about it, velocity, again, is going to be a function of your height. Velocity is a function. Velocity, okay, will determine the height. So velocity is a function of height. Yeah, is a function of height. Of height. Okay, final height, the height only. Okay, they have all the same height. That's why the speed is going to be the same. A lightweight object and a very heavy object are sliding with equal speed along a frictional surface. They both speed up. Which object resists to a greater height? What? Hold on, what? Let's read this more carefully. A lightweight object and a heavy object are sliding with an equal speed along a level frictionless surface. So here you go, frictionless, heavy object, light object. Which they will slide on a frictional surface, so F mu equals to 0. There's a V here. Which object resists to height? Which object resists to a greater height? So now let's say resist to a greater height. Well, it's a trick question, I believe. Yeah, I think it's both the same height because if you think about the kinetic energy, like the formula, if you think about, so here it's going to go from a level to a greater height, right? So it goes from a energy 1 is equal to energy 2. It goes from a 1/2 mv squared is equal to mgh. But notice the masses get canceled out. So again, velocity is going to be determined, right, by, there's a relationship between velocity and height only. Okay? Right? And in this case, so yeah, it's just they both slide to the same exact height. Doesn't matter. It all depends on its speed, and it has equal speed. So it has equal speed. All right.